Hello, my name is Sam Cathcart, and I will be presenting the research which I am currently working on with Dr. Baker. Dr. Baker and I are studying the data collected using a specific technique called MuSR, which can be used to study defects in things such as semiconductors. MuSR stands for muon spin rotation. Muon spin rotation uses muons as it implies, but it specifically uses muonium. And muonium acts like a light hydrogen isotope, and by that it means that it acts like an isotope of hydrogen, but it's a lot lighter because it's made out of muons, which are smaller than hydrogen atoms. And these molecules are shot at a target, which makes them spin polarized. So the spin is in a specific orientation or direction. And these are then implanted into a sample. In our case, the sample was a cadmium oxide powder. And when they're implanted into the sample, they can then interact with the local environment of the sample and the different nuclear moments within the sample. In order to make sure that the spin polarized or the muons interacting with the sample and the environment of the sample, to make sure that that specifically can be studied in the data which we have, zero field runs were used, which means that a small magnetic field was applied to eliminate the presence of other fields at the site of the sample. By doing this, the polarized spin can be studied to see how it fluctuates in response to the local magnetism within the sample, because if there's no magnetic field on the outside or at the side of the sample, the muons will go into the sample with the polarized spin, and then once they get into the sample, it can be studied how their polarized spin is affected by the actual sample once they're in it. Whereas in things such as transverse field runs, there's a magnetic field at the side of the sample, which causes the muons to spin, or muon spin to change before they even enter the sample. The muons, when they are implanted in the sample, they hit the front and they hit different sensors, which are in the front and the back, which produces asymmetry versus time graphs. And these asymmetry versus time graphs can then be fit with different equations to give to analyze the data and give amplitude versus temperature graphs. And these amplitude versus temperature graphs show different hydrogen sites within the cadmium oxide lattice. As seen by the fit which I found, this graph shows that there's two different amplitude signals, or two different muon sites or hydrogen sites within the cadmium oxide powder lattice. Therefore, the amplitude shows how many muons go to each site as the temperature increases. So as the temperature increases, in my specific fit of this cadmium oxide data, as the temperature increased, the muons seem to all go to one specific site, which was mu1, as seen here by the mu1 signal. As the temperature increased, the total amplitude, as seen by the blue, all of the amplitude was converted to mu1, so that means that all of the muons started to go to the mu1 site as the temperature increased, whereas as the temperature increased past around 500 right here, the mu2, the other hydrogen site, none of the muons seem to go to that one. Along with the amplitude versus temperature graphs, the fits also produced delta graphs, and the delta tells the magnetic moments which are seen and detected within the sample, which is done using the spin polarization, as previously mentioned, with the zero field runs. The higher that the delta is means that there are higher magnetic moments or magnetic influences in the actual sample. a change in the delta or the decrease in a delta means the muons are moving between sites. So the time at magnetic sites and non-magnetic sites is averaged, which decreases the data or the delta. And due to this, the change in the delta indicates there is motion of the muons going between the different sites. In the graphs above, my delta from my fit starts out extremely high. And then it starts to decrease, and this is a result of the data having an oscillation in it. As you can see, it seems like it's almost oscillating here, which is a result of the delta or the data itself, the asymmetry versus time graph, actually having an oscillation in it. Whereas a Kubo-Taiabi, the fit which I used, it doesn't oscillate. It has an initial curve, and then it dips and flattens out. Or it has an initial dip. It dips like this, and then it flattens out. Whereas the data itself seemed to almost have an oscillation, a damped oscillation, where it got smaller like this. And in the future, I plan to fix this by fitting the data with a Kubo-Taiabi, but also for the first part of the data in the lower temperature range to have a frequency oscillation on it, so that it can fit that the oscillation better. And then afterwards, I can turn that signal off because that specific site is no longer there, and I can just use the Kubo-Taiabis, which will produce and yield a better fit. As discussed previously, the fit which was generated from the data can be improved to be more accurate, and in the future I plan to do this by using the frequency oscillation as I discussed, and using this fit we can start to determine how many hydrogen sites are in the cadmium oxide lattice. This can be used to study and analyze the effects of these defects on the transparent semiconductors, because transparent semiconductors, which is what cadmium oxide is, and since we identified how many specific hydrogen sites there are and at what temperatures they show up and whatnot, we can start to study and analyze where these sites show up and how they affect the semiconductors overall, and how they affect how efficient they are.